Welcome to Chapter 5, Newton's Laws of Motion from the OpenStax University Physics Volume 1 textbook. This is for Aquinas Physics with Calculus. And today we will, of course, be going over Newton's Laws of Motion. As with all presentations and lectures I do for this class, I'm going to be using the OpenStax slideshow, OpenStax created presentation, and jumping back and forth to the actual book itself. Continuing on with the disclaimer, this is meant as a resource, not as your only source of this information. Please utilize anything and everything that helps you succeed in this class. With that being said, I will be discussing certain in particular questions. I'm not going to go over every single question in the textbook. If you have need for a better understanding of some of the material, you should read the textbook. I'm also going to highly encourage you to comment, talk to your fellow classmates, just do what you need to do to catch up if you're not following the material. This is a continuation of the previous couple of chapters. We're building on top of what we've already learned. A lot of the math is the exact same here, breaking down to XYZ components, doing some trig, all that jazz. Just now we'll get into a bit more of the real-world application and a bit more of the quantitative side of things as opposed to purely qualitative. So, what are Newton's laws of motion? Well, let's start by talking about the application. Newton's laws of motions dictate how things move and why they move. In essence, they are the foundational idea of the forces: force that pushes, force that pulls. Right. Here we have the Golden Gate Bridge, one of the longest suspension bridges in the world. And what's holding up the road? What is holding up all those cars? Well, there's only two pillars there, right? And those two pillars aren't what's holding up the road. It's that cable going all the way across. Those taut metal lines are what's holding up the road. How does that stuff work? Well, tension, Newton's forces, they explain all of that. Isaac Newton, of course, one of the most famous scientists of all time. If you ask someone to name a scientist, Isaac Newton's good chance they're going to say his name, right? He published a lot of this work in that Latin stuff in italics there in 1687. He was one of the pioneers of the modern idea of science and, did a lot of good work, right? In this chapter and going forward, we're going to do a lot of free body diagram conversations. I believe we've discussed free body diagrams a little bit, but basically a free body diagram, as shown here, explains what's happening to an object and the vector and the direction and the orientation, the scalar that it's actually happening. So if those two figure skaters are pushing that one in the center, even though the force is coming from behind her, like if the force from F2 is coming from her back, the free body diagram has it going out because that's the force being imparted on her. It's an easy way to take a complicated looking question and simplify it down. So make sure you understand how A and B are related. It's very important to doing force work and really a lot of everything we do in this class. Free body diagrams, of course, can have all sorts of variety to them. B there is at an incline. Those can all be adjusted out. Again, I want to point out here that W stands for weight and the N stands for normal force. I'll get to those at the end. But the weight is always down because the weight is gravity. Gravity always pulls us down. If you're on the side of a hill, gravity is pulling you down with respect to the earth, not down with respect to the hill, right? We want to go over things such as tension and force. These are, such as tension and spring force. There we go. These are all just forces. Everything we're going to talk about in this chapter has the same basic idea. Something is either being pushed or being pulled. What does the free body diagram show about it? And what can we derive from that conversation to calculate the result? I am, as I said before, going over and skipping questions. So if I skip a question and you want to dive into it, go ahead and dive into it, right? Newton's laws of motion describe, as I said, literally everything. The reason that you can sit in that chair is Newton's laws of motion. Well, or rather, I should say, Newton's laws of motion describe how you're able to like sit in a chair. What's actually happening when you sit in a chair? Newton's laws describe that. And of course, we use Newton's laws of motion and expanded things beyond that to make predictions and complete results. How hard you hit the hockey puck with the hockey stick is dictated by what you want the hockey puck to do. If it's a short pass, you're going to hit softer. A long pass, you're going to hit harder, right? And you are naturally doing many of Newton's laws of motion when you, for example, strike the hockey puck. And when we get to the equations and I explain each individual law, I'm sure it'll make more sense. It probably does. This stuff's all very intuitive, but we're just going to throw the math behind it. Air hockey tables, another example. Yeah, cool. Kind of going over the same thing over and over again here, right? So here we have two examples, a parked car and a moving car. How do Newton's laws apply to the parked car? Well, funny enough, one of Newton's laws, Newton's first law of motion is actually, I'll just leave it there. Newton's first law of motion is things at motion continue in motion, and things at rest stay at rest, and that's acted upon by an outside force. The car A, the fact that it's not moving means that there is no net force acting on it. You have to move something for it to move. But you have to apply a force to something for it to move. Your keyboard, your computer in front of you is not moving right now with respect to you, with respect to the desk, right? But if you take and you move the keyboard, you're putting a force on the keyboard or the computer, which is causing it to move. Car B there, it does have a velocity, but is that velocity a result of a net force? It's a good question, right? That leads into Newton's second law of motion, which is force is equal to the mass times the acceleration, F equals ma. If you apply a force, you result in an acceleration, not, I repeat, not a velocity, because Newton's first law says something in motion will stay in motion unless acted upon by an outside force. If something is moving, it's not going to speed up or slow down unless something causes it to speed up or slow down. Again, these are all very imagine, like we're not dealing with air drag force and all that, right? Vacuum chamber sort of stuff. Yeah. So what is the net result of, what is the net force on car B that even though it's going 50 kilometers per hour? Well, if it's not accelerating, the net force is probably still zero. And then you can do various, as shown here, very complicated free body diagrams explaining what's going on and simplify them out. I think the top one is a very good example of how complicated free body diagrams can be and how complicated free body diagrams can be and how simple this process becomes. You have all these forces pushing this car and it's friction and a whole bunch of stuff moving this car. And you can take all the force lines, the force vectors from the explanation, and you can clump them all together, and then a simple reorganization of what you're looking at results in a very pretty free body diagram. That third one over here on the right is a lot easier to understand mathematically than the first one with the car and the people. Yep. So this is more examples of the same song and dance. This is actually a good example of Newton's second law of motion as well. The F equals ma. We talked previously about the acceleration part of F equals ma, force equals mass times acceleration. This is an example of the m, mass. When you apply a force to something, the mass and the acceleration are proportionate to one another. So the smaller the mass, the faster acceleration, or the larger the mass, the slower the acceleration. If you pass a basketball to someone, the mass of the basketball is very small compared to the force, so the acceleration is very large to compensate. However, if you apply that same force to, say, a truck, trying to push a truck, the mass of the truck is very large relative to the force, so the acceleration of the truck will be very, very small, right? What's easier to push around, a basketball or a truck? The force, the same force being applied, they both experience an acceleration, but the truck's acceleration is much, much smaller, barely noticeable, I would wager. So that's a lot of, again, I want to reemphasize this stuff is intuitive. You know that it's harder to push a truck around than it is to pass a basketball. You know that. The reason why is the equation F equals ma. That's the explainer to that intuitive, well-known, obvious statement. So let's do some math now, try to corral all this stuff together. So example A, suppose that the net external force, push minus friction, net external force, so I've done some math for you, exerted on the lawnmower is 51 newtons, or about 11 pounds of force. And that force is parallel to the ground. If the mass of the mower is 24 kilograms, what is its acceleration? So, important thing here, I didn't cover it too much previously. The unit of force, the SI unit of force is the Newton. And it is a metric unit. So, if you're dealing with newtons, you're dealing with kilograms. And you're dealing with meters, and you're dealing with seconds. So, how do we solve that problem? Well, I give you a force, I give you a mass, I ask for an acceleration. So, we come across a equation that has force, mass, and acceleration. Fantastic. Rearrange the soft acceleration, we get 2.1 meters per second squared. The math is super easy, as I keep saying. This is all about writing down your knowns, finding your equation, solving for your unknown. Right? You can continue to apply. Again, this is a question I'm skipping. Check out the textbook if you want more in detail. You can apply this in a variety of ways, and a combination of creating accurate free body diagrams, knowing your knowns and your unknowns, and finding an equation that solves your knowns and your unknowns and fits with your free body diagram is how you solve these problems. Very complicated looking questions, such as 5.4, which I'll go over, are in fact pretty easy to solve once you follow the steps as I laid out. So, before space flights carry astronauts, rocket sleds were used to test aircraft, missile equipment, and the physiological effects on human subjects at high speeds. These things were real. They just strapped a bunch of rockets to the back of a train, let it fly off, and it's awesome to watch these things. They consisted, well, of a platform of what I just said. Calculate the magnitude of force exerted by each rocket, called its thrust, T, the force imparted by a rocket, we call that thrust, as shown in the figure below. The sled's initial acceleration is 49 meters per second squared. Mass of the entire system, we'll get to what that means later on, is 2,100 kilograms, and the force of friction opposing the motion is 65 newtons. Friction is something we'll dive more into later, but for now, let's take the information and let's solve what we need to solve. So that top diagram looks cool, but is confusing, right? We have all these different arrows going every which way. We got purple arrow. Let's take this information and shrink it down to a free body diagram on a classic Cartesian coordinate system. So what is moving? So what is moving? The rocket is moving. The rocket is moving just in one direction. It is moving to the right. Okay, cool. I don't have to worry about it moving up or down, all that jazz, irrelevant. So what arrows are involved with forces, right? Because acceleration is not a force. Acceleration is the product of a force. So I have 4 rockets, each providing equal thrust, and they're all in the same direction. 1, 2, 3, 4. I have friction opposing the direction. It says right here, the friction of 650 newtons is opposing the motion. The rocket's moving to the right here. Friction, by definition, is pushing it to the left. And then normal and gravity are affecting the ground here. The normal is pushing up. The weight is pulling down. So why is the normal pushing up and the weight pushing down? When we get to Newton's third law of motion, I'll explain a bit more. But there's a free body diagram. Let's solve it. Cool. So we were given numbers, right? We were given an acceleration, a mass, and the force opposing friction. All right. So what can I do with this information? Well, I know I'm given an acceleration and a mass, and I know there's a force pushing it to the right, but I don't know what that number is. However, I do know the force pushing it to the left, right? So if I can figure out how much force is being pushed to the right, I can subtract out what's being pushed to the left, and what's left over after I subtract out the force of the friction pushing to the left is the force of the thrusting, the force of the rockets. How do I figure out the total force? Well, F equals ma, because I know my acceleration and I know my mass. Lucky for us, this is pretty easy to solve, right? Because your mass and your acceleration are knowns, m and a, right? And the total force as shown here is the thrust of the rockets subtracted away from the force of the friction. So F net equals 4t minus F, because 4t is in the positive direction, F is in the negative direction. And there's 4 t's because there's 4 rockets each doing t amount of thrust. Plug and chug in my information, solve for my unknown, in this case t, and there we go. Pretty simple. 2.5 times 10 to the 4 newtons. That's a lot. Right? It is quite large, yes, as said in the significance, but it's also accurate. I mean, it's a rocket, right? It should be large. You can deal with these sort of questions with angles. And again, do your SOHCAHTOA. We talked about this in previous chapters, right? Break it down into X, Y components, solve for what you need to solve for. These are questions in the textbook. Feel free to go to the textbook if you want a deeper dive into this. But we're not talking about anything different. We talked about from the 2-dimensional and 3-dimensional forces conversations from previous chapters. It's the exact same thing, just for kind of caring about the real world example as opposed to just saying something's moving. Go to 5.8 and dig into it a bit. Here we go. Mass and weight. So 5.8, clearing a field. A farmer is lifting some moderately heavy rocks from a field to plant crops. He lifts a stone that weighs 40 pounds, about 180 newtons. What force does he apply if the stone accelerates at a rate of 1.5 meters per second? So this question is interesting because it has an unknown variable. It tells you the variable, but it doesn't explicitly tell you the variable. The variable that's not telling you is the resultant force of gravity. Because what is gravity? Well, gravity is what pulls us down. And gravity is directly affected by our weight in kilograms. The heavier you are, the more gravity pulls you down. Right? That's how a bathroom scale works. Gravity pulls you down the bathroom scale, and the bathroom scale tells you how much gravity is pulling you down. The heavier you are, the larger the number. The lighter you are, the smaller the number. Right? So that question includes a example of gravity, and it's found in that about 180 newtons section. So we all know the force applied to lift a stone, a certain acceleration that weighs so much. So what's going on here? Well, this 3x diagram here explains it, right? What forces are impacted onto the stone? Well, we have weight pulling it down because gravity pulls down on everything with 180 newtons of force. And then we have some force picking it up. That force picking it up causes the net force to create an acceleration of 1.5 meters per second squared. Cool. Weight equals mass times gravity. And we know the mass, and we know the weight, or the force of the gravity, W. We know gravity is constant, 9.8 meters per second squared. So we can determine the mass of the boulder to be 18 kilograms based on that gravity component. Cool. So, or I guess you could have converted 40 pounds into 18 kilograms, but let's do it the math, the physics way, right? So what forces are impacting on the boulder? Well, the force of you picking it up minus the force of gravity pulling it down. We know the force of gravity pulling it down, so we can solve for the sum of the forces, the force picking it up minus the force pulling it down, and that has to equal the mass times the acceleration. We know the mass is 18 kilograms, so the acceleration is 1.5. Solve for F. We landed about 207 newtons, or we can round up to 210 newtons. That's those significant figures. There you go. Again, the math is simple. You just need to take your equations and rearrange them to solve what you need. You were given an unknown, you were given more than one variable by telling you that the force of gravity is 180 newtons, because the 180 newtons force of gravity also tells you the weight of the boulder in kilograms. Newton's third law of motion is the equal and opposite forces motion. Any motion, any force impacted on something has an equal but opposite force also impacted on it. Meaning, when you are swimming and you push off the wall, you are putting a force on the wall, and the wall is putting an equal force, equal in amount, back on your feet and therefore your body. The reason you take off and accelerate away from the wall is because your mass is way smaller than the pool's mass. So the pool doesn't have a lot of acceleration. You do instead. If you do things that are more equal in mass, they both bounce off of each other, right? The classic example is a cannon. Load up a cannon with a cannonball and fire it, the cannon recoils back, right? Or a rifle, a gun. These things recoil backwards from the force because the mass is not that different from one another. This third law of motion combined with the first two, again, describe the reality of physics around us. And anything and everything you do, you can actually describe with this conversation, right? And it's you know that physics works, it's intuitive to your life, but it's cool to think about the rationale and the math behind it as you go about your day. Every step you take, you imparting so much force into the earth is imparting equal force back to you. You have an acceleration because you're smaller than the earth. The earth technically has an acceleration too, but it's so minuscule, so minor, that it's basically undetectable. Every time you step, you're pushing the earth down a little bit, which is cool. So, yeah, all this stuff plays the same. The change in weight you feel when you're in an elevator, all of that jazz, Newton's laws of motion. Cool. So let's take this concept and let's apply it to a more mathematical approach. Let's look at reference frames, and let's look at the way that different systems interact with each other to achieve somewhat different results. Go through the book again. I am skipping chapters. There's the math behind Newton's third law in case you needed it. I am skipping questions because I want you to go and look at these questions to solve them if you need the help. Choosing the correct system. A physics professor pushes a cart of demonstration equipment to a lecture hall, as shown here. What a nice physics professor. Her mass is 65 kilograms. The cart's mass is 12 kilograms, and the equipment's mass is 7 kilograms. Calculate the acceleration produced when the professor exerts a backward force of 150 newtons on the floor. So if she's pushing into the floor with 150 newtons backwards, the floor is pushing her with 150 newtons forward, right? All forces opposing the motion, such as friction and air resistance, total a measly 24 newtons. So calculate acceleration given all those variables. So what's going on here? Well, we have the professor pushing the cart, when we have the cart and the professor fighting friction and what have you, air resistance. So 3-by diagram we're talking about looks a lot like system 1 up here, where the force of the professor pushing the cart is the force of the floor pushing the professor, and therefore the professor pushing the cart is very large. The cart is not moving vertically up and down, so normal and the gravity are canceling each other out, and the friction's fighting it just a little bit. The wheels are kind of squeaky, So how do you solve that problem? Well, same thing you've been doing, F equals ma. You know the acceleration, you can figure out the mass, and you can use that to solve the force. The force is 2 components we care about because the thing's only moving horizontally. And those 2 components are the force of the professor and the force of the force opposing motion, such as friction and air resistance. So set up your equation, F equals ma, solve for the unknown force, which is the force of the floor. And there you go. the unknown acceleration, which is A, because you know the force of the floor and you know the force of gravity, the force of friction. Wow. So that middle equation there solves for the net force, 126 newtons, again in the right direction, or the eastward, the positive x direction. Mass, add up the masses and accelerate based on the knowns. But given that information, can you calculate the force the professor exerts on the cot using the data previously done? So what's the difference here? Well, the first one is calculate acceleration produced when the professor exerts a said force on the cot. So the cot's mass and what the cot is doing is connected with the professor. But if we care about the cot and not the professor, how does that change things? Well, the professor no longer has to worry about certain things like their weight, right? Since if the cot's the only system I care about, system 2, the inner circle here, I have less I have to deal with because I don't have, for example, the force of her feet anymore. Her hand is the only thing applying force. The feet, which are connected to the hand here, don't have the same aren't doing the same thing. They're going the same direction, but not doing the same thing. And we can look at the math here and see what I'm talking about. We define the system of interest as the cot plus the equipment, as shown, as I said before. So the net external force of system 2 is the force the professor exerts on the cot minus the friction. The force she exerts on the cot, as we said before, is the external force, and the force professor is internal to system 1, but is external to system 2. So we can care about Newton's second law of motion for this because we still have a net force being applied. So what force is she impacting on the cot? We know the force that her feet are putting on the ground, but how much force is she putting into the cot? So again, we don't care about her weight in this, so we just care about the cot's weight. We know how fast the cot's moving. So if we can figure out the net force on the cot, subtract out the net force of the air resistance, we can land on how much force the professor is actually doing. Again, it's the same conversation we've been having over and over and over again. Find out your variables, find your equation, set it up correctly. Take some time, think about it, right? She is imparting 150 newtons of force to move at whatever acceleration we calculated, 1.5 meters per second. She is imparting 150 newtons into the floor, but that's because she is moving herself along with the cot. The cot itself is only feeling 53 newtons of force because the other 147 or 107 newtons of force, whatever it is involved with her moving herself. But she's a lot heavier than the cot, right? That's why we're breaking the system into two separate parts, separate her from the cot. We can go over lots of examples of forces interacting with each other. And the forces applied on M1 are different than the forces applied on M2, things like that. And we can have these conversations with a variety of things. This is what I was referencing to earlier, the idea of normal force and gravity. When you put the dog food on the table is in fact pushing the dog food up as much as the dog food is pushing down into the table. It's not moving because the forces are equal, so the net force is 0. If you don't have a net force on something, Newton's first law of motion says nothing about it changes. The dog food doesn't move because there's 0 net force on it. There's still forces impacting the dog food. Gravity is still pulling it down, but since the table is pushing up equally, nothing happens. Here's a classic I'm skipping for this conversation here. A skier going down a hill. What's actually happening? Fun part about this question, I'll do another classic here in a bit, is that even though the skier is on an angle, in this case 25 degrees, gravity still points down negative y, straight down. Gravity doesn't go down at 25 degrees, it goes straight down. So you got to break it down into your components, right? We've talked about that a lot. I instead, and there's a better example showing again sine and cosine, right? We've talked about this a lot. Almost there. We'll instead talk about the tightrope walker here in a bit. Tension is another way to say force. In this case, picking up an object, your hand's moving up, so the rope's being pulled down, the weight, what have you. It's all free body diagrams. It's all F equals MA. They're just different ways of asking the same questions. Tension, of course, is important in, say, biology. It's how your muscles work, right? But at the end of the day, at a kind of basic level like this, you're doing the same math. This is the thing I keep saying to you over and over again. At this level, the math isn't like overly complicated. You just need to follow some basic trigonometry. And the thing that's going to catch you, the thing you got to make sure to do right, is organize your information correctly. So let's go over the tightrope walker, as I said before. And here we go. Cool. Calculate the tension in the wire supporting a 70-kilogram tightrope walker as shown below. So we have a tightrope walker in the center of the tightrope, and to either side of the tightrope walker, the rope itself is being bent at a 5-degree angle. So what is the tension on the wire? Well, tension is the force, essentially. So we want to calculate the force on each wire that is caused by a 70-kilogram object, in this case a person, pulling it down to 5 degrees from level. So in order to solve this, as I've said in the previous chapters, it's important to take this complicated looking triangle and break it down into X and Y components, I hat and J hat components. Because once you break it down in X's and Y's, everything in the X is in the same direction, everything in the Y is in the same direction purely. So that way you can add and subtract them and everything will stay consistent. And then when you reconstruct your triangles at the end, you have exact measurements. So resolving that tension is SOHCAHTOA, right? The X, this tension LX and tension LY is the left side of the tightrope walkers, X and Y components of that 5-degree bend. And something that's not explicitly stated but should be understood by looking at the question in the picture, the tightrope walker is not moving. So again, it's not explicitly stated, but unless you are told an acceleration or you are shown in some way an acceleration, your net forces in all directions are 0. Everything that's happening in the tightrope walker needs to 0 out, which is why this free body diagram here is so interesting. The left and the right, the tightrope walker is not moving left or right. So those two equal in the X direction, but the weight pulling him down is exactly equaled by the Y components of the rope pulling him back up, Newton's third law of motion. And since Newton's first law of motion, if you're not moving, you have no forces, that tells you F equals ma, F is 0. Sorry, A is 0. So if A is 0, you can figure out the forces required to make A 0, right? So break down your left and right forces into X and Y components, shown here, right? Cosine, the X components are cosines, the Y components are sines. And then once you break them down into actual numbers, as shown here, you can solve for the total tension. And the tension, remember here, there's a left tension and there's a right tension. And you should be able to intuit this. If they're equal on both sides, then they're equal, right? So the left tension, the left tension and the right tension are both half of that weight component. And we can figure out his weight because we know how heavy he is and we know gravity, right? So we can figure out the force down, and the force up needs to equal the force down. So that's what's going on here with the F net Y conversation. The net force in the Y direction is equal to the left tension in the Y direction plus the right tension in the Y direction minus his weight. And we solved for the Y components of that tension with the sine thetas. So add all that stuff up. Notice we have 2 T's in this conversation. So here's your 2T here, right? Solve for your tension. Some quick, simple math. Then you had tension of 3,930 newtons. The math isn't hard. It's setting up and understanding what you're doing. If you break things down into components, as shown here, you won't get lost because your math is always going to be following what you stated. Break it down into components, realize the told to you parts that aren't explicitly told to you, like net force is 0, and solve. If you're given an acceleration, net force is not 0, right? The previous questions, I told you a total force, or I told you an acceleration. The physics teacher pushing the cart full of stuff, I told you an acceleration, so you could figure out a net force after that. Zoom in on what I was talking about. You can keep doing this question over and over and over again. It's the exact same conversation. Here you can talk about solving for thetas, right? Spring tensions, same conversation. It is all about finding that equation and making it work. When we get in the next chapter, we'll go over the constants involved with these things. And this stuff, what I talked about here in very simple terms, again, applies to like everything about the world and how it functions. The way storms work follow the basic laws of physics. Everything you do, Santa's sled follows physics and all that jazz, right? And all of these things can best be understood and best be solved by taking a slow, concentrated approach, doing good note taking, good free body diagrams, good knowns and unknowns, cataloging things correctly. Take your time, write it down, and you'll get there just fine. So when you run into questions like this, you can say, well, M1 has some things going on, and M2 has some different things going on. The force being applied is only being applied to M1. M2 receives the force from M1, but M2 does not receive the force itself, right? They're pushing against each other. And that is something that may be important depending on what you're doing or the question being asked of you. Here's an example 5.16 to go over the importance of this free body diagram conversation a bit more. They have this whole big long section of rules to follow with free body diagrams. All of these words are broken down and just simply take your time and make sure you're doing it right. If you're trying to rush through this stuff, you're going to screw it up and it's going to just hurt you more down the road. Cool. So a block rests on the table, right here, the blue one, as shown. A light rope is attached to it and runs over a pulley, right here. The other end of the rope is attached to a second block. The two blocks are said to be coupled, so they're attached, right? One moves, the other moves. Block M2 exerts a force due to its weight, gravity is pulling it down, which causes the system, two blocks in a string, to accelerate. Cool. So, can you draw a free body diagram for each swing? Well, first of all the things accelerating. Well, it says here that the system is accelerating due to the mass of block 2. So, again, something that's not explicitly stated but should be intuited is that not all the force scalars, not all the lengths of the arrows should be equal. Since you have an acceleration, you therefore have a force being applied. And that force, the net force, is not 0. So when we come down here to our solution, we notice that we do in fact have forces being applied. M2 has a downward force and a tension force pulling it up. The tension force comes from acceleration. It's not super obvious because they drew it real close, but the tension arrow is in fact shorter than the mass arrow because the block is being pulled down. And then block M1, the green block, does also experience that gravity down. But block M1 is not moving down, so the normal force of the table it's on is pushing up an equal measure. N and M1G are the same. And the rope is pulling it to the right, so you have a tensional force, the exact same tensional force that's on M2 is on M1, but they're in different directions. And using that information, you can, in fact, solve these problems if I would have asked you a question. And that's chapter 5. application problems word, paragraphs to ask questions, but it all boils down to the same basic principles, right? Write your stuff down, draw a good picture, take your time, find your equations that solve what you need to solve for. All this stuff is intuitive, but make sure to think about your problems. What if I have a question with more than one unknown, do I actually know something that's not being explicitly told to me? Right? This question here, you're told that they accelerate, but you're not like explicitly told that the net force is not equal to 0. You have to realize that. Thanks for watching.